Picture this, right? You've just built an API, you've pushed it to production, the deployment pipeline flashes green, and honestly, it is running beautifully.
Best feeling in the world.
It really is.
Right.
You're looking at your monitoring dashboard, and the server CPU is calm, the database is just humming along without a care in the world.
Barely breaking a sweat.
Exactly. And your average response time is a blazing fast 42 milliseconds. You feel like an absolute rock star.
Oh, yeah. For now, anyway.
Right, for now. Because then a massive marketing campaign hits, or maybe a viral post goes out, and suddenly you send 10,000 concurrent users at this API all at exactly the same second.
And we all know what happens next.
The system just freezes.
Yeah.
The dashboard lights up red with timeouts.
Yeah.
And so the mission for today's deep dive is figuring out, well, what actually breaks first in that scenario?
It is honestly the ultimate nightmare scenario for any back-end engineer. But it's also where the most fascinating architectural lessons live, I think.
Oh, completely.
Because we tend to think of our code as this pristine, logical environment, right? Where execution flows exactly as we wrote it. But under that kind of extreme pressure, physics just takes over.
Physics and hardware limits.
Exactly. Hardware constraints, network limits, queuing theory, they completely hijack your application's behavior. It stops being about the code and starts being about the plumbing.
So to really get into the mechanics of why this happens, we need to set up a specific baseline for a system under load based on the source material we're looking at today.
Let's do it.
So let's look at a standard configuration for a framework like Spring Boot. In our scenario today, the application server has been configured with a capacity of 200 request handling threads.
Okay, 200 threads.
Yep. But the database connection pool only contains 10 connections.
Right. And those numbers, those specific numbers, are going to dictate everything that follows in this scenario.
So we should probably put a quick disclaimer on that, right?
Oh, yeah, definitely. I should clarify for anyone listening that 200 threads and 10 connections, they aren't like universal mandatory defaults for every system out there.
Right. It depends on your setup.
Exactly. Your specific framework, your cloud infrastructure, the nature of your workload, all of that will dictate your actual config.
But for the sake of this deep dive, we're using 210.
Yeah, because the absolute digits aren't actually what caused the outage. The outage is caused by the drastic ratio between those two resources.
So a ratio of 20 to 1.
Exactly. We have massive capacity to accept work, right? 200 threads. But just a tiny straw, those 10 connections through which to actually complete the work.
Okay, so let's trace the happy path first, just to see how this is supposed to function. Under normal conditions, everything works perfectly.
Right, it's totally fine.
You've got 200 threads ready to handle incoming web requests and 10 database connections standing by. If a single user logs in and requests, say, their order history, the system just breezes through it.
It's highly efficient by design. That single request hits the server, one of those 200 available request threads picks it up and starts executing the controller logic.
It parses the payload, runs through the service layer, all that good stuff.
Yeah, exactly. And eventually it reaches the point where it needs actual data. It needs to talk to the database. So the thread asks the database connection pool for a connection.
And since it's the only one asking, the pool just instantly hands over connection number 1.
Yep. The thread borrows that connection, fires off the SQL query across the network, retrieves the results set, and...
This is the critical part, right?
It is. It immediately returns that connection back to the pool. The application thread then builds the JSON response, sends it back to the user, and the whole transaction wraps up in that 42 milliseconds.
Super clean. And even if we scale this up to 10 concurrent users hitting the API at the exact same millisecond, the system is still completely stable.
Totally fine.
All 10 users hit the endpoint. 10 of our 200 request threads spin up and start executing. They all reach the database layer simultaneously.
And since the pool has exactly 10 connections, it hands 1 to each thread.
So every connection is actively doing useful work.
Right. Data is moving, the database is processing queries in parallel, the connections are returned, and the system remains perfectly healthy.
Okay, but let's push it to the breaking point. This is what we're here for. What happens when 100 concurrent requests arrive?
It's interesting.
We have 200 threads, so the web server itself has no problem accepting all 100 incoming connections. The code starts executing.
The server happily assigns 100 request handling threads to execute the application code. But remember the constraint we established?
The 10 database connections.
Exactly. Eventually, every single one of those 100 threads is going to need to talk to the database to fetch that order history,
So the first 10 threads hit the pool, and they grab the 10 available connections.
leaving 90 threads basically stranded.
Right. Which leaves 90 threads holding a request, but with no way to talk to the database. Now, if I'm an engineer relying on a modern, robust framework, my intuition here is that the application will just recognize the sudden load.
You'd think so, yeah.
I mean, it should just automatically spin up more database connections to handle the rush, right? The framework knows we need more capacity, so it should just allocate it.
That intuition is incredibly common, and it completely misunderstands what a database connection actually is.
Oh, really?
Yeah. The application will not exceed the configured pool limit of 10 just because the server is busy. It doesn't care. We have to violently separate the concept of a thread from a database connection in our mental model.
Break down that separation for me. Why can a framework casually spin up 100 threads, but it absolutely refuses to spin up more than 10 connections?
So a thread is relatively cheap. It's basically an execution context managed by the JVM or the operating system. It takes up a little bit of memory, sure, but creating one is a really fast local operation.
Okay, so threads are cheap.
Yeah. Very cheap. A database connection, on the other hand, is a massively heavy, persistent network link to an entirely different piece of physical infrastructure.
Are they all different beast?
Exactly. Establishing a new database connection requires a TCP three-way handshake across the network. It requires TLS negotiation for security.
Right, a whole handshake.
The handshake, the authentication. The database server itself has to allocate dedicated memory buffers and a dedicated process just to manage that single socket.
Oh, wow. So you definitely don't want to be doing that on the fly while a user is sitting there waiting.
Exactly. That's the entire reason connection pools exist in the first place. You establish those 10 heavy connections at startup and keep them open because creating them dynamically is just too expensive.
So when that 11th thread asks the pool for a connection, the pool doesn't create one. It just tells the thread to wait.
Yep, sit and await.
Which means we now have 90 threads that are technically active in the application, consuming memory, holding on to variables, but they are completely frozen.
Doing absolutely zero useful work.
They are essentially standing in line.
You have officially hit your queuing bottleneck.
Okay, let's scale this up to the actual nightmare scenario, the 10,000 users we talked about at the top of the deep dive. Traffic surges.
Here we go.
We go from 100 users to 1,000 to 5,000 to 10,000 incoming requests. If I'm looking at my traffic metrics, I see a massive spike of 10,000.
Okay, we have to debunk a massive misconception right here before we even look at the database again.
What's that?
10,000 incoming requests does not mean 10,000 requests are simultaneously executing inside your Java or Node application.
Right, because the execution capacity itself is bounded by our 200 threads.
Exactly. When those 10,000 requests hit your infrastructure, they shatter across different stages of the system.
Like where?
Well, your load balancer might hold some. The operating system's TCP backlog queue holds a bunch of them. Inside the application server, you only have 200 threads. So only 200 requests are actively executing code.
And the other 9,800.
The other 9,800 requests are just trapped at the front door, basically waiting for a server thread to even become available.
Wow. And of the 200 that actually are executing, maybe 10 are running database queries.
Yep, the lucky 10.
The other 190 are trapped inside the application, holding a thread, but waiting in line for a database connection.
That's the reality of it.
You know, I think a restaurant analogy maps perfectly onto this queuing problem.
Oh, I love a good analogy. Let's hear it.
Okay, so our application server is the restaurant. The request threads are the waiters. We have 200 waiters on staff.
Okay, pretty big staff.
Very big.
Mm-hmm.
But the database connections are the stovetops in the kitchen, and we only built 10 stovetops.
I see where this is going.
So a massive bus pulls up, and 200 customers walk in. Our 200 waiters happily take all 200 orders simultaneously. The web server is doing its job perfectly.
It's taking the orders.
Right. But then all 200 waiters rush into the kitchen at the exact same time to get the food cooked.
With only 10 stovetops available.
Exactly. 10 waiters get their food cooking. The other 190 waiters are just standing around in a kitchen window, staring at the chefs, doing absolutely nothing but holding a ticket.
It's burning time.
And meanwhile, There are 9,800 customers outside banging on the windows who can't even get a waiter to talk to them.
That perfectly captures the mechanism of a constrained system. It really does. Now, let's look at the customer in your restaurant, the user clicking a button on their phone,
The ones banging on the window?
or the ones whose waiter is stuck in the kitchen. Why does the application suddenly feel incredibly slow to them? This is what we call the illusion of latency.
Because they're just waiting for a stovetop to open up, right?
Yes. If you look at the database monitoring tools, the actual SQL query might still only take 30 milliseconds to run. The chef is still cooking the burger in exactly the same amount of time.
So the database thinks it's doing a great job.
It really does, but the user doesn't care about the chef's individual prep time. The user doesn't look at their screen and say, wow, my SQL query executed in 30 milliseconds.
No, of course not. They don't even know what a SQL query is.
Right. The user experiences, I clicked the button and I stared at a spinning wheel for 4 seconds. Response time is not just execution time. Response time is the entire agonizing journey.
The waiting in line.
All the lines. The request arrives, it waits in the TDT queue, it finally gets a waiter, a thread, the code runs. Then it needs the kitchen, a database connection, it waits in the pool queue.
And then finally, the query executes in 30 milliseconds.
Yes. Then the response is built and sent back over the network.
So as the contention grows, you can literally trace this cascade of latency. It starts at a healthy 42 milliseconds.
Beautiful, fast.
Then the line forms at the connection pool, and suddenly requests take 180 milliseconds. And the web server threads fill up, and users are waiting at the front door, pushing response times to 900 milliseconds.
And it just keeps climbing.
Then 2.4 seconds. Until eventually, the load balancer or the browser just gives up, and you get a timeout.
Because under extreme load, waiting becomes infinitely more expensive than the actual computation. The CPU is fast, the database disk might be fast, but the traffic jam is what kills your application.
When you explain it like that, the bottleneck is glaringly obvious. I mean, if I'm the on-call engineer, my Datadog dashboard is glowing red and users are timing out, my first instinct is going to be the easiest, most logical fix imaginable.
Oh no, I know what you're going to say.
If the problem is that 10 connections aren't enough for 200 threads, I'll just open my configuration file, change the connection pool limit from 10 to 200, and redeploy.
Don't do it.
Why not? We have 200 waiters, let's just buy 200 stovetops. Problem solved, right?
That is the most tempting trap in software engineering, and it is incredibly dangerous.
But if the bottleneck is the 10 connections, why shouldn't I expand the pool? I mean, Postgres can easily handle a few hundred connections.
Because you haven't magically created infinite system capacity. You've just moved the bottleneck further down the chain.
Moved it where?
To the
Atlas.
database itself.
Yeah.
Let's say you increase the pool from 10 to 50 to 200. Yes. The waiting time for a connection inside your Java or Python application will instantly decrease.
Right. The waiters aren't standing around the kitchen window anymore.
So throughput improves, at least initially.
Okay, so what's the catch?
Temporarily it improves, but now you've unleashed 200 simultaneous highly concurrent queries directly onto the database itself. And the database has finite physical resources.
It's not infinite.
Right. It has finite CPU cores. It has limited memory for caching. It has mechanical limitations on disk I/O.
Let's upgrade that restaurant analogy then.
Yeah.
We didn't just buy 200 stovetops. We crammed 200 stovetops and 200 chefs into the exact same small kitchen.
Now you're seeing the real problem. Those 200 chefs are physically bumping into each other. They're dropping ingredients. They are spending more time fighting over the spatulas than actually cooking food.
That sounds like a mess.
It is. In database terms, this is lock contention and context switching.
Context switching is basically the silent killer here, isn't it?
Absolutely. If your database server only has, say, 16 CPU cores, it can only mathematically execute 16 things at the exact same physical microsecond.
Right.
If you throw 200 heavy queries at it simultaneously, the CPU has to rapidly juggle them. It pauses query A, saves its state to memory, loads the state for query B, executes a fraction of it, pauses it, and moves to query C.
That's the context switching.
Yes. And the CPU is wasting time just swapping the tasks instead of actually doing the math.
So 100 concurrent complex queries are not automatically better than 10.
Not at all. By opening the floodgates, you push the database CPU to 100%. Cache lines get trashed, rows get locked, causing queries to block each other.
Oh, man.
Suddenly, that SQL query that used to take 30 milliseconds now takes 4 seconds to execute, simply because the database itself is thrashing.
So I didn't fix the bottleneck at all.
No, you just made the database grind to a halt, which is actually much harder to recover from than an application queue.
Okay, so changing the connection pool to 200 is a trap. Let's attack it from the other side then.
Let's hear it.
If my 200 threads are getting backed up and timing out, what if I just bump the web server up to 1,000 request threads? Let's just hire a massive army of waiters to process the incoming traffic faster.
And what exactly are those 1,000 threads going to do when they hit that exact same 10 connection pool?
Right. They're going to hit the exact same wall.
Yeah.
They'll just wait in line, but now the line is 5 times longer.
Exactly. They are just going to pile up. And worse, they add immense overhead. Each of those 1,000 threads requires memory allocated on the JVM heap.
Which eats up RAM.
Yes. And having 1,000 idle threads sitting around increases the burden on the garbage collector. You are actively degrading the application's performance just to have more things waiting.
Just paying for a longer line.
Right. Which brings us to a fundamental rule that every developer needs to internalize. More concurrency does not equal more throughput.
So if the scarce resource is downstream, like our database, adding more upstream concurrency just creates a wider traffic jam.
You get more contention, more memory overhead, and more waiting. That's all.
Wow. Okay, so we can't just change a 10 to a 200 in our config file, and we can't just crank up the threads. So what are we actually supposed to do when a system locks up in production? Like, what is the correct number of threads and connections?
You know, that is the #1 question asked on developer forums, and it is entirely the wrong first question.
Really? Why is it the wrong question?
Because you cannot fix a constraint until you know exactly where the constraint lives. The first question must always be, where is the system actually spending its time?
Okay, so we need a solid diagnostic mental model. If I'm looking at my observability platform during an incident, what metrics actually tell the truth? My instinct is just to look at the average response time spiking.
Yeah, don't do that. Averages are liars. You need to look at latency distribution, specifically your P99 and P95 metrics.
Wait, why is the average a liar?
Imagine your application gets 100 requests, right? 90 of them hit a cached endpoint and return in 5 milliseconds. Super fast.
Okay, 5 milliseconds is great.
But 10 of them hit the database bottleneck and take 4,000 milliseconds. If you average that out, the average response time is around 400 milliseconds. An engineer might look at that and think, well, 400 milliseconds isn't great, but it's not an outage.
But meanwhile, 10% of your users, which, if you go back to our viral traffic scenario, could be 10,000 people, are staring at broken screens.
Exactly. The P99 latency tells you what the worst 1% of your users are experiencing. If your P99 is 4 seconds, you have a severe problem, even if your average looks totally fine.
Because the outliers are where the queuing bottleneck reveals itself.
You have to see the outliers.
So beyond latency distribution, we need to trace the wait times.
Yes. You need to measure database connection wait time. Like how many milliseconds is a thread sitting in that pool queue doing nothing?
Right.
You need to look at pool utilization. Are you actually maxing out the 10 connections constantly, or are they idle? And you absolutely have to look at the database itself. Is the CPU saturated? Are there heavy disk reads?
Because if the root cause is that a single SQL query takes 3 seconds to execute because it's doing a full table scan, giving it a bigger connection pool won't fix anything.
No, it just lets you run more slow queries at the exact same time.
Right. The solution depends entirely on finding the constraint first. If you identify the real bottleneck, the fix might not involve tweaking a configuration file at all.
Exactly. It might mean adding a missing index to the database so that slow query runs in 5 milliseconds instead of 3 seconds. Or it might mean adding a Redis caching layer so 80% of your traffic never even asks for a database connection in the first place.
Or, in extreme cases, it might even mean introducing back pressure, literally rejecting incoming requests at the load balancer with a 503 service unavailable code.
Which nobody likes to do.
It sounds harsh to drop traffic, I know, but telling a user, hey, we're too busy, try again in a minute, is infinitely better than letting them crash the entire database layer and taking down the system for everyone.
So true. When we step back and look at the whole board, the crucial realization here is that every single request moves through a chain of bounded resources.
Right, from start to finish.
Network bandwidth, incoming request queues, server execution threads, CPU cycles, heap memory, database connections, database locks, disk I/O.
It's a massive chain.
And every single link in that chain has a hard, physical, or configured limit.
And the moment demand exceeds the capacity of any single link in that chain, something has to wait. When waiting grows, latency grows. When latency grows, users get impatient, and what do? They hit refresh.
Which is the final nail in the coffin. The thundering herd.
The thundering herd.
Yes. Users hitting refresh spawn brand new requests, demanding new threads and connections, while the server is still desperately trying to process their original abandoned requests,
It just adds exponential load.
leading to cascading system failures.
It really puts it into perspective.
Yeah.
Under light traffic, you're just looking at your neat little lines of Python or Go. You're looking at business logic. But under heavy traffic, the code just fades away, and you start seeing the system. You are looking at network pipes, CPU cycles, and lock contention.
I always say the code is just the instruction manual. The system architecture is the reality.
The system is the reality. I love that. So to wrap this all up for you, we set out to answer what happens when 10,000 users slam into an API with 200 threads and 10 database connections.
And we found our answer.
We did. The answer is that those 10,000 requests are forced into a brutal competition for bounded resources. And whichever resource runs out first, in our scenario, those 10 database connections, ends up dictating the latency and stability of the entire architecture.
That tiny connection pool acts as the ultimate choke point. It protects the database from melting down, but it sacrifices the web server's responsiveness in the process.
It's a trade-off.
Yeah.
We spend so much of our careers as engineers trying to perfectly tune these numbers. We tweak the threads, we resize the connection pools, we adjust CPU allocation limits, all in an attempt to eliminate waiting and maximize throughput.
It's what we do.
But I know you had a final, somewhat philosophical engineering thought to leave us with regarding that pursuit of perfection.
Yeah, I do. Think about the logical conclusion of all this tuning, right?
Okay.
If you somehow perfectly configure your system so that every single thread, every single database connection, and every single CPU cycle is maxed out at exactly 100% utilization and absolutely nothing is waiting.
It sounds like a dream.
But is it? Have you actually built a perfectly efficient system? Or have you just built an incredibly fragile house of cards where a single 1 millisecond network hiccup or garbage collection pause will instantly trigger a catastrophic, unrecoverable, system-wide failure?
Wow. If there's no slack in the rope, the moment it pulls tight, it just snaps.
You need some idle capacity just to absorb the shock of reality.
That is definitely something to chew on the next time you're looking at a production dashboard, where everything looks just a little too perfect. Thank you so much for joining us on this deep dive. The next time you deploy an API, we hope this conversation helps you look beyond the syntax and deeply into the physical systems you build every day.